Hello everyone, my name is Emre Akbaş. I am an assistant professor at the Department of Computer Engineering, Middle East Technical University. Welcome to my talk at the Beyond MAP Reassessing Evaluation of Object Detectors workshop at ECCB 2020. I'd like to thank the workshop organizers for inviting us to present our work here and giving us the opportunity to disseminate our work. The title of my talk is Unified Evaluation and Training of Object Detectors using Localization, Recall, Precision, or shortly the LRP metric. As you might have guessed from the title of my talk, I will first talk a bit about average precision, or AP, which is the de facto evaluation standard in object detection today. I will certainly criticize AP. I'm going to talk about its weaknesses. And then I'm going to introduce you LRP, the Localization-Recall-Precision metric, and which I will argue that addresses all the weaknesses of AP. And then finally, I will talk about unified evaluation and training of object detectors using LRP, where the same objective function is used both for training and testing of evaluation. And this is joint work with this awesome team, which includes our brilliant students, Kemal Öksüz and Barışcan Çam, and my awesome colleague, Sinan Kalkan. So average precision, or AP, is today the de facto evaluation measure for not only object detection, but also other visual detection tasks like instance segmentation and key point detection. So it has sort of a central importance. Let's first recap how AP works or is used for evaluating object detection. First, our input image goes through an object detector and it outputs a set of detections. And here, each element of this set is a two-tuple containing a score SI and then the coordinates of a box, bounding box BI. And then, of course, we are given a set of ground truth boxes as well, the set G. And for the sake of simplicity, let's assume that there's only a single object class. So there are instances of that object class in the images, or the rest is background. The first step towards calculating AP is the filtering the detections given a detection threshold. So we first discard detections with lower confidence scores and keep the rest in this set DT. Then we match the elements in DT with those in G based on the intersection over union criterion. And here typically intersection over union greater than 0.5 is used. After the matches are identified, now we can categorize the detections and ground truths as true positives, false positives, and false negatives. Detections matched with ground truth are true positives, unmatched detections are false positives, and unmatched ground truth are false negatives or misses. Once we have these counts of these categories, once we have these numbers, we can compute recall and precision. And recall is the number of true positives divided by the cardinality of the ground truth set, and the precision is the number of true positives divided by the cardinality of the detection set. Once you have these two values, it becomes a point in your recall precision plot. And when you do, after you do a systematic sweep on T and repeating the steps above, you'll get a recall precision curve. And the area under this curve is known as average precision, or AP. And this is the de facto evaluation measure used in object detection. Here, we only gave a theoretical description of how AP is calculated. I'm skipping all the practical details, Pascal style AP, Coco style AP, and a bunch of other stuff. So this is only a theoretical description, which will be ground for discussions in the later, the rest of the talk. So let's talk about the weaknesses of AP. There are a bunch of weaknesses of AP, and by the way, this is not an exhaustive list. We listed here only the most important ones, especially the first three are major weaknesses. So let's look at them one by one. So first, AP does not measure localization quality. So any match detection, that means any detection with intersection or union with a ground truth greater than tau, contributes to AP by the same unit amount. And this unit amount does not depend on localization quality. So as long as your detection has an intersection over union larger than tau, for example, 0.5, it doesn't matter whether the intersection over union is 0.6 or 1. The current solution for this weakness is to use COCO-style AP, which uses different values of tau and calculates APs for these different values, and then you obtain the final AP by averaging these APs. This is certainly a way of including localization into the evaluation, but still the localization quality is not explicitly measured here. Similarly, AP does not explicitly account for false negatives. As you know, unmatched ground truth boxes are false negatives or misses, and these are not taken into account. These are taken into account only implicitly. The final AP does not tell us much about the rate of false negatives or 1 minus recall, because recall is implicitly included in the AP by averaging precision at regularly spaced recall values. So I'm going to show an example where this will become, I think, clear. And that's because of false negatives are not explicitly accounted for. We have another measure for measuring recall, which is average recall, and shortly AR, because of this weakness of AP. AP cannot distinguish between different error cases, and these are certainly connected to the first two weaknesses. Let me illustrate this with an example here. Here we see three different sets of detections for the same image, hence for the same ground truth. The ground truth boxes here are shown with red colors, and then there are a total of 4 of them in these images. And then the blue color denotes true positives and green color denotes false positive. So below each image, you can see the corresponding recall precision plots. Let's look at examples one by one. In the first example, 2 of the ground truth boxes are recalled successfully, and there are 2 misses or false negatives. In the second example, all ground truth boxes are recalled successfully. You see blue boxes, which are true positives for each of the ground truth boxes. Plus, there are some high confidence false positives. Therefore, precision is not perfect to begin with for early recall values, and it stays the same for later recall values as well. In the third case, again, all ground truth boxes are successfully recalled, and some of them with low confidence detections. And then we have some low precision. We have some false positives again. And here, the situation is a little bit different from the second case. We have high precision at early recall values and low precision at later recall values. So given these pretty diverse scenarios, AP is the same for all 3 cases. The area under the curve for these 3 plots are 0.5. They are the same. So obviously, AP cannot distinguish between these 3 different error cases. Another weakness of AP is related to the practical issues. The precision values need interpolation. What does this mean? if you literally follow the theoretical description that I gave at the beginning of my talk to plot your recall precision curve, you'll probably get a curve with lots of zigzags, like the one here. It is now a common practice to sort of remove these zigzags from the curve by interpolation. So at each point, for example here, you basically find the max precision to the right of that point and then take that max precision as the precision value at the current point. So this way you'll get a much nicer looking recall precision curve without the zigzags. Why is this a problem? Why are these zigzags a problem? Because the area gap between the interpolated curve and the actual zigzag curve might become significant, especially for classes with few examples. And this is a real problem even with big data sets such as COCO. For example, in the minival data set of COCO, there are only 9 instances for the toaster class. So this effect can get pretty significant. And finally, AP cannot be used to evaluate hard predictions. Let me make it clear first, what do we mean by soft or hard predictions? Soft prediction is a prediction with a confidence score. Exactly like what we have in typical object detection, where a detection output means a bounding box and a confidence score. A hard prediction means no confidence scores. In that case, you can only have a pair of recall and precision values. So you cannot get a curve out of them. For example, panoptic segmentation is such a task where for each pixel you predict a class and an ID if needed without any confidence scores. Okay, so it can be argued that AP is an average of precision values over confidence scores, and precision can be used instead in this case. However, using only precision over hard predictions does not yield a consistent performance since both localization and recall performance are ignored in this case. Okay, so this was the last item in the list of weaknesses of AP. Now let's see how the localization recall precision metric addresses all of these weaknesses. So LRP is a solution that successfully addresses the weaknesses of AP. It explicitly accounts for localization, quality, and false negatives. It can distinguish between different error cases. It has intuitively interpretable components, and it does not need interpolation, and it can evaluate hard predictions. Also, as a bonus feature, LRP is a metric, and we know that AP or 1 minus AP is not a metric. And being a metric is a good to have property. It satisfies the reflexivity, symmetry, and triangle inequality properties. And this is important since metricity implies consistent distance definitions over performance measure domain. Okay, let me introduce LRP metric here. So it is an error metric that considers both localization and classification. Given a set of ground truth boxes G and a set of detections D, as usual, we first match the elements in D to the elements in G using the intersection over union criterion. And then after the matches are identified, we can now label each detection as either a true positive or a false positive, and each ground truth as a true positive or a false negative. Up to here, we did not do anything new. The procedure is the same as that of average precision. But now let's define LRP. LRP can be intuitively defined as the total matching error divided by the total sources of error, or maximum possible error. And formally, here is the expression for LRP. So let's look at the terms one by one. The first step is accounts for the localization error. And these other two, they account for the classification error. Here, each true positive, which means a detection that matched with the ground truth, is its localization quality. This LQ function stands for localization quality, and we use intersection over union for object detection. We measure its localization quality, and 1 minus LQ is the localization error. And we just sum these errors over true positives, and then any detection detections that are not matched with ground truths are false positives, and they contribute, each of them contribute to as 1 to here, and then each unmatched ground truth contributes as 1 to this count number of false negatives. The Z here is a normalizing constant, and it reflects the total sources of error or maximum possible error. And let's take a moment to understand how this expression Z calculates the total error, total maximum possible error. So given the detections D and ground truth G, what could be the worst case? The worst case could be when there are no matches, right? When there are no matches, all of the detections will be false positives, and all of the detections will be false negatives, and then you will have as a total error the summation of the false positives and false negatives, and the number of true positives will be 0. But when there are matches, again you count the unmatched detections as number of false positives, unmatched ground truths as number of false negatives, and for the matches, they contribute to the LRP by their localization error. And here tau is the criteria, the threshold that is used in the intersection over union criteria, which is typically taken as 0.5. And consider a true positive that has a very low localization quality. Let's say its intersection over union with the ground truth is 0.5. Then you'll get 1 minus 0.5 here and 1 minus 0.5 in the denominator, and you'll get a 1, which is the highest possible contribution to the error. If the localization quality is great, that means you have an intersection over union of 1, then this denominator will be 0, and this true positive will contribute to 0 to the LRP error. Another way to express LRP is with using explicit components. So it's the same metric expressed in a different way. And this this expression emphasizes its components. It emphasizes that there are 3 components: the localization error, recall error, and the precision error. And here the localization error is the average localization error of your true positives. Recall error is the 1 minus recall, which is 1 minus the number of true positives divided by the cardinality of the ground truth set. And this corresponds to the false negative rate. And the precision error corresponds to the 1 minus precision, and this corresponds to your false positive rate, number of false positives divided by the cardinality of the detection set. So you can use LRP for tasks that has hard or soft predictions. LRP can be directly used for hard predictions. It's straightforward. You just evaluate the expression in the previous slide, and that's it. There are no difficulties there. For soft predictions, for example, object detection, remember the case with average precision where we do a systematic sweep on the detection threshold and we get the recall precision curve. Similarly here, we do a systematic sweep on the detection threshold, and then we get T versus LRP values, okay? And from that T versus LRP values, you can calculate two different things. One of them is optimal LRP, OLRP for short. And this is basically the minimum LRP value along that T versus LRP curve. And the other is average LRP, which is just the average of LRP values that you get for different detection thresholds. LRP can be applied for other tasks as well, tasks other than object detection. Here we show 4 examples, key point detection, instance segmentation, and panoptic segmentation as extra examples. For example, let's take key point detection. All you need to do is to just find a suitable and appropriate localization quality function here, to plug in here. And OKS, object key point similarity, is an appropriate localization quality function for this problem. And then I might have missed a minus here, sorry for that. And then you plug this into your LQ and you're done. A typical example of this problem would be human pose estimation, and then you can now directly use LRP for that problem. What about panoptic segmentation, which is a relatively new problem introduced in CVPR 2019 by Kirillov and others. It is a task with hard predictions. So for each pixel, the method just predicts labels without any confidence scores. That's why it's hard predictions. And the authors introduced panoptic quality for this task. And here is panoptic quality. And if you notice, it looks very similar to LRP. And please note that panoptic quality is proposed after LRP. Let's look at LRP versus panoptic quality on an example. An image from the COCA data set, and here we see its segmentation mask with the purple color. And from left to right, these vertical bars correspond to intersection over improvements by 0.1 increments. So every slice, with every slice from left to right, intersection over union improves by 0.1. And at these values, we plotted panoptic quality with red and LRP with green color. And as you can see, LRP behaves smoothly while PQ makes large jumps. And PQ is not a metric, but LRP is. Actually, PQ cannot be a metric because it's a higher, better measure, but 1 minus PQ is not a metric. So for other results and for more experimental comparison of AP and LRP, I refer the listeners to our original paper from ECCV 2018. And there is also an example application where a still image object detector is extended to a video object detector by using LRP as a method to produce optimal detection thresholds per class. It's an interesting example, and we show that LRP here is very effective. So due to time constraints, I cannot give these extra results here. So this concludes the first part of my talk where we discuss AP and LRP. Now I'm going to talk about unified evaluation and training of object detectors. Let's first look at the current situation. The typical paradigm today is to use, during training, smooth L1 for localization and cross entropy or focal loss or some variant of cross entropy for classification. And for testing or during evaluation, you use average precision. So there's a clear discrepancy between training and testing here. During testing, you want to maximize your average precision, but during training, you want to minimize smooth L1 and cross entropy, a weighted combination of them. There's a clear discrepancy. These things are of course correlated, but they're not the same. And also, there's a disconnect between localization and classification during training. Smooth L1 is trying to make the localization better, but it doesn't care about the classification quality of examples. And similarly, cross entropy is trying to improve the classification without really taking into account the quality of the localizations of those examples. So this, I want to illustrate these discrepancy and disconnect on a toy example. So consider the following set of detections and assume that the ground truth set cardinality is 4. We have 4 ground truth boxes and 10 detections. And these detections have confidence scores from 1.0 to 0.1. Let's say we match these detections to our 4 ground truth boxes, and suppose, just assume, the first, third, sixth, and 10th detections are matched with ground truth, so they are now true positives, and the rest of the detections are false positives. What we need next is the intersection over union between the true positive detections with their ground truths. And let's assume this is just one case. The intersection over union values are like this. If you notice, the detections with higher scores have higher intersection over union values, and the ones with the lower scores have lower intersection over union values. You can have another situation where the reverse is true. The higher, the more confident detections have lower intersection over union scores, and the lower confidence one have better localization. So let's evaluate this using the average precision, which is the current standard. And we evaluate AP for different taus for 0.5, 0.65, 0.8, and 0.95. And here you see the corresponding AP values. When we average them for the first case here, the AP turns out to be 0.37, and for the second case, the AP turns out to be 0.2. Which makes sense because in the first example, the localization quality is better. I mean, the higher confidence detections have better localization. So this makes sense. Let's look at the same configuration during training. Suppose we are using smooth L1 and cross entropy, and if you do this calculation, you will see that for both of these cases, smooth L1 will give you the same values and cross entropy will give you the same values, because these loss functions just look at their tasks individually, independently. They don't care about, so the localization branch doesn't care about the classification quality of the examples. So here you can see the discrepancy. The evaluation for the same configuration, the evaluation is telling us one thing, and the training losses are telling us another thing. In the training, we cannot distinguish between these two cases, but the evaluation does. Let's see what ALRP does for this example. You can see that ALRP gives 0.53 for the first case and 0.89 for the second case. And remember that ALRP is a lower is better metric. And these are consistent with the AP values. So if we can somehow use ALRP for both training and evaluation, then not only we address the discrepancy between training and testing, we can also remove the disconnect between the localization and classification losses. The discrepancy between training and testing has recently been addressed by AP loss by Chen and others in CUPR 2019, and smooth AP by Brown and others in this ACC 2020. These are definitely great progress towards unifying training and testing, but because of the weaknesses of AP, there is still this discrepancy that I talked about between localization and classification in these approaches, unfortunately. These are great steps ahead, but because of the weaknesses of AP, they are not immune to the weaknesses of AP, let's say. Okay, we are arguing here that with LRP, we can achieve truly unified evaluation and training. We propose to use ALRP for both training and testing. And in that way, there is no discrepancy between train and test objectives because they are the same thing. And there is no disconnect between localization and classification. And they are handled in a unified manner during training. But how do we minimize ALRP for training? It's a ranking-based function, and how do you minimize it, right? The answer to that question is can be found in the recent AP loss work by Chen and others. In this work, the authors try to minimize AP directly, okay? So they create this AP loss, which is 1 minus average precision at tau 0.5. And now this becomes a loss function, so lower is better. And you can express AP in terms of the ranks of your positive examples with respect to their confidence scores. So this rank plus means the rank of your ith positive example among all positive examples, and rank I is the rank of your ith positive example among all examples, including negative ones. So this way you can write AP loss as a summation over your positive examples. You can further write this as two summation loops. One, the outer loop is on the positive examples, the inner loop is on the negative examples. And you get this simple expression where H is a unit step function here. So if its argument is positive, it returns 1, otherwise it returns 0. Xi here is a transformation of the detection scores. Xij is the detection score of the jth detection minus the score of the ith detection. And here, this H, what does it do? If the detection score of the jth example is higher than the detection score of the ith example, this will return 1, otherwise it will be 0. So there are a few steps between these, a few derivation steps between these two steps. So I'm not showing everything here, but the important conclusion here is that you can write AP average precision loss, which is 1 minus AP at a certain tau, as a summation over positive examples and negative examples over this term, which the authors call primary term, which equals this. Now, how do you minimize this? That's the question. And if you write the derivative of the AP loss with respect to the detection score of the ith example, we can expand this using the chain rule just as simply as this expression. Now, this is no problem, right? The transformed scores, derivative of the transformed scores with one of the scores is easy. And then the rest of the chain would go to your backward through your network. This is a problem because this expression includes lots of step functions because of the ranks. You can, here rank values are expressed as the summation of unit step functions, right? We are counting things larger than u or below than u. So because of all the step functions here, you cannot, this is not differentiable. And the way the authors of AP-loss overcome this obstacle is to use error-driven update from the perceptron training. So this gradient is basically replaced by this value here, minus delta xjk. And let me explain what that is. So delta xij is the update on your xij, which is a replacement for this gradient here. And here the error-driven update from the perceptron learning method is used, where you basically subtract your current value from the target desired value. So this Lij AP star is the target or desired value for your primary term, and you subtract your current value from this, and this is your error-driven update. And the target desired value here is 0, because when the ith and the jth examples are ranked appropriately, then you don't have an error. That's why you have 0 there, because this will be 0. And 0 minus Lij AP gives you minus Lij AP. Once you replace this gradient with the error-driven update, then the rest is a very simple expression, and the rest is just gradient descent. So we apply the same error-driven update technique to ALRP loss. In order to be able to do that, we first write ALRP as a summation over positives, and this is nothing but a rearrangement of the ALRP loss. And you can write the LRP loss on the ith positive as using this expression. As you can see, the error at the ith positive example depends on the number of false positives above that having scores larger than that example, the localization error of that particular example, and also the localization errors of the positives that have larger scores than the ith positive. So that's why LRP is doing this unified localization and classification. So we further expanded and write the ALRP loss as two nested summations here. The outer loop is over the positive examples, and the inner loop is over the negative examples. And this is the primary term for ALRP. Now, once we have this, we can use the error-driven update to write the error-driven update, which will replace our derivative of the cost with respect to the detection score. And here we write the target value here first, and then subtract the current value from it. In ALRP, if you remember AP loss, the target was 0, it's 0 error, but in ALRP, this is not simply 0 because of the localization error, and we get such an expression. And you can compare this with the error-driven update of the AP loss, and this is our update with ALRP loss. And the fundamental difference is that localization is included into the picture. So when you are, for example, taking the gradient of your loss, ALRP loss, with respect to classification scores, it creates gradient for your localization branch too, because it is in this gradient, the localization errors of the positive examples that are that have larger scores than the ith positive are included. So that's why we say ALRP handles localization and classification in a unified manner. And the result, doing this, it improves performance on COCO. ALRP improves its baseline AP loss more than 4 AP points, and it outperforms all one-stage detectors. I cannot give a full table here because this is under review right now, but it's working pretty well. And there are not only this performance improvement, there are advantages to ALRP optimization. One of them is the number of hyperparameters. This table shows you the loss functions of the state-of-the-art object detectors, many of them. And as you can see, the number of hyperparameters are large. Compared to these methods, ALRP loss has only one hyperparameter. Another advantage is that the training of ALRP loss is balanced in the sense that the total gradient magnitude with respect to the positive examples and the total gradient magnitude with respect to the negative examples, these are the same in ALRP. And this is a theoretical result, which we further show empirical here. And this plot shows you the iteration versus this total magnitude of gradients with respect to negatives divided by total magnitude of gradient with respect to positives. And as you can see, these are standard deviations. Both cross entropy and focal loss have large variations, but ALRP loss is just constant. So as a summary, AP is the de facto evaluation measure for object detection, but it has many weaknesses. LRP metric addresses all weaknesses of AP. LRP can be used as a loss function to train object detectors, thereby unifying evaluation and training. LRP optimization is balanced. LRP optimization has just one hyperparameter. So as a conclusion, use LRP. I hope I convinced at least some of you to try LRP in their projects. Thanks for listening. If you want to try LRP in your projects, you can just go to our GitHub repository and download the code. Before closing, I'd like to mention another workshop in ECCV 2020. It is the imbalance problems in computer vision. I'm an organizer in this workshop, and I'm mentioning this here because the audience of the Beyond MAP workshop might be interested in this workshop as well. So please come and visit our workshop too. Thanks again for listening.